Hello and welcome to our first lesson in chapter 4 where we work with two variables. We've been working with just one variable up to now. We've been measuring things and seeing how much they change and spread and summarize. Now we're looking at two variables, and what we want to think about is how one variable depends on the other. So we're going to have independent and dependent variables. So let's look at a situation that we can try to make some sense of here. And if we look at this graph, this is the main thing to do is get the big picture. Karen's running a marathon. She is going a distance and it's taking her time. So how all this fits together into one kind of main idea is very helpful. How many miles had Karen run after 3 hours? So, or I'm going to say at 3 hours. At 3 hours on the time axis, that's our independent variable, she is 12 miles into her marathon. So 12. And we really should use units. Hello and welcome to our first lesson in chapter 4. It's called bivariate data analysis. We've done univariate or one variable where we looked at one measurement and said what was happening and looked at measures of center and spread. Now we're going to look at how one variable can change because another variable changed. There's like a relationship, and what we talk about is an independent variable does something and then the dependent variable changes because of that. This dependent variable will not change unless the independent variable change. So a good example is if you get paid so many dollars per hour, let's say $10 an hour, then how much money do you make depends on how many hours you work. And the hours you work is, we would say, is independent. So the independent variable will be the thing that's happening and time happens and then something is a result of that. So if we try to make sense of this, we've got Karen's marathon. So this is mentally, you should be imagining someone's going on a pretty long run and they're covering a distance, and how far they are in the marathon depends on the time. So the time in hours is going to be independent. How far she is in the marathon is dependent. Right. So how many miles? Right now we're going to get good at reading a graph, and then we'll talk about kind of the math involved. How many miles had Karen run at 3 hours? So if you go to 3 on the x-axis and go up to the graph, you see that she has run 12 miles. How long did it take for Karen to run 21 miles? Now we're looking at the distance she's run and trying to work backwards to see how long it took. So 21 miles is when she's here, and that happened at this point, which is 5 hours. How long did it take Karen to finish the marathon? Well, she's finished when she stops out here, and that took her 6 hours. Which leg of the marathon did Karen run the fastest? Now, this is where it gets a little complicated. We have to know the rate or rate of change, and she's running faster or slower, and sometimes it looks like she's even stopping. She's not getting anywhere, but time's going by. So what we're looking for is a steepness, and if we look here, this rate of change is 6 miles per 1 hour. Then this one's clearly slower, and I could figure that out. It's 3 miles per 1 hour, 3 over 1, and that's rise over run. And then if we look over here, this is hard to say, but I'm going to say from 2.5 to 4, that's an hour and a half. She's traveling from 9 to 18, so that's 9 over 1.5. Then it looks like 0. I should have mentioned that this interval C here looks like she's just resting. And then another slope with a different steepness. Looks like we could estimate that to be an hour and a half to go from 18 to, I don't know what a marathon is, 24 point something. But so if I look at that, I say 18 to, I'll call it, or 26, I think. I'm going to call it 26. So this kind of an unfair situation, but 18 to 26 is 8 miles in 1.5 hours. Well, if we're looking for her her steepest, to go 8 in an hour and a half is not as fast as going 9 in 1.5. 3 in an hour isn't as fast as 6. So it's going to be one of these two, or maybe they're the same. This is 6. That's pretty obvious. 1.5 goes into 9 6 times. So she is actually going her fastest in two places. Interval A, where she's at 6/1, and interval D, which is 9/1.5. So two places she's going her fastest. In context of what Karen was doing at E on the graph, how do we make sense of that? In an E interval, she is 18 miles away at 4 hours and at 4.5 hours. She's going nowhere. So in context, and this might be the hard part of the question, we calculate numbers pretty easily and compare numbers, but what's the meaning is going to be a challenge in this chapter, as anytime we do word problems. So an explanation is she was resting. She is traveling. She's making no progress towards getting at the end of the marathon. So we can assume she's resting or visiting with people or getting a drink. But I'm just going to say resting, and that's an acceptable answer. So when we talk about all these things that we can kind of visualize, there's a math context. And what we talk about here is for a rate of change, you might be used to the word slope. We want to talk about what is the rate that things are changing. In this case, how far she's getting away from her starting place, and then how close she's getting to her ending place. We would say that the rate of change is a rise over run, or I'm going to use this triangle called delta. It means change in the y coordinate, that's the rise, and then the change in the x. And sometimes it's just y over x. That's a special case with something we call direct variation. But if you focus on a change in y over a change in x, like I showed here, this 9 was a change in y, that was the change in x. That is the rate of change for that interval. So once again, x-axis, we always put the independent variable. Time is pretty hard to control. It does what it does. But something that we don't necessarily have control over is an independent variable. The dependent variable we use in the vertical or y-axis, that's something that often a distance or a pay, some amount that is depending on how much time we've spent. And that can change, but time and distance or time and money, that's a typical application. A steep increase is going to be something that from left to right goes up pretty quickly. Oops. Oh, jeepers. Pretty quickly, compared to a less steep, which would be increasing still, but not as quickly, so the steepness. And then the decrease, instead of being, well, I'm going to jump down to constant. Constant, these are all a constant rate of change, but if my position is a constant, I'm not moving, like here, from 4 to 4.5 hours, her position was constant, 18 miles. It didn't go up, didn't go down, so it wasn't an increase or a decrease. That would be a horizontal line. And then finally, a decrease would be something that is going down. So increase steeply, increase gradually, decrease maybe steep, or we could do a gradual as well. And then constant means the position does not change. The rate might be constant as well, but where we are will not. Okay, let's try to apply some of this. So in our classwork, we talk about what parts of the graph show the person increasing their distance from home. So their distance from home at 0 seconds is 0 miles. They're nowhere away from their house because they haven't started traveling. Once they start traveling, as time goes by, the dependent variable distance from home is increasing. They're leaving their home. So what part of the graph shows increasing? This is an increase from home. A works. B is not increasing or decreasing. It's remaining 3 miles from home. So we wouldn't count that. And then C is another place where we're increasing our distance from home. Finally, we rest. And then now we're decreasing our distance from home. And then resting and then decreasing. We're getting home. So in 10 hours, we've gone 8 miles away from home in kind of a not consistent way, but whatever, we're out for a bike ride. And then once we get 8 miles away, we decide we do some stuff and then we come home. What part of the graph shows the person is stopped? Well, if they stop, they are not getting any further away or closer to home. So these flat lines have a zero rate of change. You're not getting further or closer. So B, D, and F are all situations where the person has stopped or at least is not getting closer or further. What part of the graph does the person appear to be traveling the fastest? And this goes back to that previous problem. The fastest is going to be the steepest slope. So the greatest change in y divided by change in how long it takes. So this one has a slope for this first interval here of 3 miles an hour. Then it's 0 miles an hour. Then it is 3 to 8. That's 5 miles in 1 hour. So that's a 5 mile per hour. Then again a 0. Then coming here, it is from an 8 down to 2. So that's 6 miles an hour towards home. And then another 0 interval. And then finally 2 miles in an hour is a 2 mile per hour. So this interval right here, E, is going to be the fastest. Turns out it's when we're getting home though. And then how far from home did the person actually travel? We talked about that. For the complete trip, even though they actually traveled 16 miles, their total distance from home never got greater than 8. So we went 8 miles to get away and 8 miles. All right, another example of how to read a graph here. We're looking at steepness of slope. I hope when you see a slide, some of the things you do in addition to listening to my explanations is think about, well, what might I ask? You know, this looks like, does this person ever decrease in height over time? No. Or if it's not a person, if it's a plant, I don't know what it is, but it's always increasing in height. This one is increasing pretty quickly, then not changing, and a little more gradual. And then this one's just constantly at the same rate, getting higher over time, higher over time. Okay, so a change, but increasing. 3 changes where one is it's just not doing anything. All right, let's read. A tomato plant grows taller at a steady pace. Steady, another word we could use is a constant pace. It doesn't change. This plant is going rise over run at the same rate. This one's doing a rise over run and then a different rise over run. So that's definitely changing. So I would say C is the steady or constant rate or pace. A tomato plant grows quickly at first, remains a constant height during the dry spell, and then picks up again. Well, this one never stops growing. It's always growing, just at different rates. This one stops growing here, so this is a B. And then finally, a tomato plant grows at a slower pace and then a quicker pace. Well, that's graph A. Consider the following graph that display the height of a flag being raised. So if you can imagine a flag going up, match the correct graph to this description. A flag is raised up a flagpole in a jerky motion using a hand-over-hand method. If you've ever seen a flag raised, it might be a custodian that goes out and they pull their arm length and then they have to re-grab it. So it goes up quickly, then there's a hesitation, then it goes up again, then there's a hesitation as they're putting hand over hand, pulling down on a rope that raises the flag. So this example is there. Write a story for each of the other graphs. I'm not going to get real interesting about this. The challenging part for these questions might be, this is a constant rate or a steady rate, but I need to hear you say, why is that happening? So I had a student do this problem and they said, a motor raises the flag at a constant or a steady rate. At steady rate. Okay, so it's not quick and then slow, it's just constantly up and over, up and over. And then for C, example C, this is, let's say, person steadily raises the flag but gets tired. And that, I say steadily, it's actually increasing at a slower and slower rate. So it's not maybe steady. I don't like that now that I said it and listen to myself. So I'm not going to say steadily. A person raises the flag quickly at first, and then gets tired. And slowly continues to raise the flag. I should have typed this out and just clicked on it. My writing's pretty rough here. But you need to get the idea that there is a steady rate, a increasing but slower and slower rate, as well as why is that happening, okay? So if it was just a pure math question, you could just say that's a steady rate, and you could say this is a decreasing rate. The rate is decreasing even though the flag position is going up. I'm slowing down as I do it. You got to say why that might happen. All right. Following graph represents Abby and her sister Brittany's distance from home at any given time. So this is a pretty common theme here, it looks like. Looks like this person ends up 2 miles away from home and then comes back. Or Abby and Brittany, two people. Complete the sentence that describes the two girls walk along the road. Abby and Brittany decided to walk from their home to the water park. So I'm going to assume the water park is 2 miles away. Oh, which is 2 miles away, because that's the furthest I get. What total distance have they traveled? 4 miles, but 2 of it is to the park and then 2 to return. When the girls left their house, they first walked at a rate of, so that's this rate. It is a half of a mile in a half an hour. Half divided by half is 1. That's a 1 mile per hour rate. After 30 minutes, they decided it was taking them too long to reach the park, so they increased their speed. So after 30 minutes, that's half an hour. This rate, you can see, is faster. Now they're going a mile and a half rise over a half-hour run. So they increase their speed to a rate of how many miles per hour? It's 1.5 divided by 0.5. Well, 0.5 goes into 1.5 3 times. So they went 3 miles an hour. That's clearly faster than 1 mile an hour. When they reached the park, they spent some time doing something. That's why they went there. Well, at 1 hour they got there, 1 hour of their trip, and they stayed till their 3rd hour of their trip. The total trip time was 5 hours. 1 hour spent getting there. From 3 to 5, 2 hours was spent getting home, and 2 hours was spent at the park. Okay? I have another slide here of the same, it's still the same situation. So when they first left the park to return home, so they're leaving the park to go home here, they walked at a rate of whatever this is. So this looks like it took them a half an hour and they went a half a mile. So that's again 1 mile per hour. After how many hours they decided to stop for lunch? Well, so this was, let's get there faster. We're here enjoying it. Okay, time to go home. Okay, I'm tired or I'm hungry. So I'm going to say this interval from 3.5 to 4 hours. So at 3.5 hours, after 3.5 hours, they decided to stop for lunch. Now it's not clear in this question. Is it after half an hour of leaving, which I kind of think is what they're getting at here, or is it 3.5 hours of their total trip? Both answers, I guess, could be right. I'm going to go with 1/2 in the context of the problem. So after a half an hour of their trip home, they decided to stop for lunch. After lunch, they finished their walk at a rate of, so this is, they're done, now they're going. So what is their distance per time? Well, their time is an hour. Their distance was a mile and a half. So they had a mile and a half to go. It took them 1 hour. So 1.5 over 1, or I'll just put 1.5 miles per 1 hour. By the way, this is something called a unit rate per one of anything. So if I said they traveled, let's see, I don't have any that take more than an hour. Well, for this one, if I said they went half an hour, sorry, half a mile in half an hour, that's the same as saying 1 mile per 1 hour. So this is complicated, kind of messy looking. We really want unit rates, so it's going to be per hour per 1 hour. That's what we want to have as our denominator, a 1. We don't like decimals for a denominator. We'll get into that in class as well. Okay, I think that gets you to your homework, and we can talk about it in class.